Welcome back to the course on electronic packaging and manufacturing. We will continue with our discussion on thermal management and cooling, and today, as I had mentioned at the end of the last lecture, we will talk about heat transfer correlations, because this is what is going to help us in determining what is the thermal resistance as a function of flow rate, as a function of temperature difference, depending on the conditions or scenario under which the application that we are talking about. Okay. So, heat transfer correlations, that is going to be the concepts that is going to be covered today. Okay. Now, the thing is, this again is probably a recap for people with the mechanical engineering background who have taken either undergraduate level or postgraduate level heat transfer course. So, but for people who have not had these courses as part of their curriculum, I will try to explain some of the terms. So, apologies if it is going to come across as something repetitive to the students with mechanical engineering background. All right. So, concept going to be covered today is heat transfer correlations. Okay. So, heat transfer correlation, before that, what is it going, or before going into some of these correlations, let us first talk about what is a correlation, okay, and what is, when I say correlation. Okay. So, most of the correlations that we will see is going to be in terms of a parameter called Nu, and Nu is something called a Nusselt number. Okay. Now, Nusselt number, what is it? It is a non-dimensional, I am going to try to keep this as simple as possible. It is a non-dimensional heat transfer coefficient. Okay. So, what is Nusselt number? It is non-dimensional heat transfer coefficient. So, what we do is we take H and then multiply it with some length scale which is L and divide it by the fluid thermal conductivity Kf. You see, if you just look at the units, this is non-dimensional, because H is watt per meter squared Kelvin and thermal conductivity is watts per meter Kelvin. So, therefore, H times a length divided with thermal conductivity is non-dimensional. Okay. Now, depending on what is L, L can be length of a surface of a plate, surface, L can be diameter of a cylinder, sphere, pipe, channel, etc. Okay. So, Nusselt number is defined in this manner. Okay. So, now I am going to define three other terms, non-dimensional terms. The next one I am going to talk about is called Reynolds number and denoted by Re. Reynolds number is a very interesting term. It's a one of the most fundamental quantities in fluid mechanics, and that is given by U L, again a length scale, or let us say rho U L over mu. So, rho is the density of the fluid, mu is the viscosity of the fluid, U is the velocity, and L is the length scale. Okay. So, again L, like before, can be length of a plate, it can be diameter of a pipe, etc. And Reynolds number determines if a flow is laminar or a flow is what is called turbulent. Laminar is when the flow happens very steadily, you have one layer of fluid, another layer of fluid, like that. Turbulence is when you have all this mixing, okay. The fluid is no longer moving uniformly in one direction, but there is a lot of churning and mixing and all that, okay. All right. I would also want to say that this transition from laminar to turbulent happens at the critical Reynolds number REC. Okay, which is typically around 2000 for flow through a pipe. In that case, L is actually dia. It is actually, some people say 3 into 10 to the power 5, some people say 5 into 10 to the power 4 flow over a flat surface, where L is the flow length. Okay. So, Reynolds number is very important, and actually Reynolds is ratio of inertial to viscous forces. Okay. All right. There is something else called, especially when we come to natural convection, there is something called Grashof number, denoted by Gr of L, and that is given by G beta T surface minus T infinity L cubed over nu squared, and this is a function of basically, or this is a measure of buoyancy forces divided by viscous forces. Okay. Just like in natural, the first one is something that helps in natural convection heat transfer. It helps the liquid to go up, or the heated fluid to go up. Viscous forces tries to hold it back. Okay. There is another thing which is completely a fluid property, which is known as Prandtl number, PR, and that is given by mu Cp over the fluid conductivity Kf. Okay. And the last one is Rayleigh number, RAL, and that is nothing but Grashof times Prandtl. Okay. Now, Prandtl, these all have physical significance, by the way. Prandtl number actually is momentum diffusivity over thermal diffusivity. So, I am not going into those details right now. Okay. I am just giving you that much details which will help you solve problems, okay, without going too much into the intricate physics of fluid mechanics and heat and mass transfer. Okay. So, let us quickly recap what we said, that these three: Nusselt number, one non-dimensional term, HL by K; Reynolds number, rho u L over mu; and Grashof, Prandtl and Rayleigh number. Okay. And then typically what we see is Nusselt is going to be a function of Reynolds, Prandtl, and maybe something else for forced convection, and it is going to be a function of Grashof or Rayleigh, Prandtl, and something else for natural convection. Okay. So, recall what we said many slides back when we were talking about force of convective heat transfer. We said that the challenge in solving convection problems lies in the determination of the heat transfer coefficient H, right. How do you determine H? You determine H by calculating Nusselt number, which is a non-dimensional form of the heat transfer coefficient, and that Nusselt number depends on the variety of parameters depending on the flow scenario. If it is forced convection, it depends on Reynolds number and Prandtl number and maybe some other geometrical features. If it is natural convection, it depends at a minimum on Grashof and Prandtl number and maybe something else. Okay. And in turn, Reynolds, Grashof all depend on the temperature, the velocity. Reynolds depend on the velocity, the fluid properties, the geometry. Prandtl depend on the fluid properties. Similarly, Grashof depends on the geometry, the temperature difference, and Prandtl of course again in the fluid property, right. Oh, one more thing I need to quickly mention is that this beta is the coefficient of volumetric expansion, and it is typically 1 over the absolute temperature of average for an average temperature for ideal gas. So, if it is air, we many a times take it as an ideal gas, and therefore, beta is 1 over the average temperature in the absolute scale. Okay. So, with this much background, what we will do is we will move back to the slides and talk about correlations. So, this functional form, what are those anyway? Okay, by the way, there is no need to memorize all this, I also do not remember most of these, but it is important to know that you have a bunch of these correlations available to you. So, the judgment as a thermal engineer depends or is really in identifying which correlation to use when, to identify the flow scenario, the situation, and have the judgment of which of these correlations. I can give you 50 different correlations, which one to choose. Okay. All right. So, flow over a flat plate. For flow over a flat plate, the average Nusselt number, and what is going to be the average Nusselt number for flow over a flat plate? Is going to be H times average Nusselt number H bar L over Kf. So, that is given as a function of is given as 0.664 Reynolds to the power half, Prandtl to the power 1/3 if it is a laminar flow. And what is Reynolds then? Rho u infinity L over mu. So, this is flow over a flat plate. Forget all this. So, you have a fluid flowing over a flat plate, and as a result of velocity, as we know, increases from 0 to the mean value as you move away from the plate. The temperature, if it is a heated plate, it is highest at the plate and then reduces and slowly takes the value of the ambient at which it came in, the flow came in. Okay. So, you will if it's a hot plate, if you bring your hand very close, you feel the warmth. If you move away, you have really come onto this range and you do not feel it, feel the warmth anymore. So, this thickness within which the temperature reduces from the hot surface temperature to the ambient temperature is known as the thermal boundary layer. and it slowly increases in thickness as you move along the flow length. Similarly, the thickness within which the velocity changes from 0 to the mean free velocity, as we call it, is known as the momentum boundary layer. And depending on the fluid, for a fluid with higher Prandtl number greater than 1, the momentum boundary layer thickness is higher than thermal boundary layer thickness. So, water is an example. For Prandtl number less than 1, like for example air, the momentum thickness boundary layer thickness will be less than the thermal boundary layer thickness. Okay. So, this is a little more detail, but probably it does not harm to know all these, and especially for mechanical engineering students, I think this is a good recap. All right. So, for turbulent flow, look at the correlation. The dependence on Reynolds number is now 4/5. So, a few things. Nusselt number is in laminar flow is proportional to Reynolds to the power half, which means heat transfer coefficient is proportional to the square root of the velocity. Clear? But in case of turbulent flow, where there is more churning, it is probably intuitive that the heat transfer is going to be higher, and therefore, the heat transfer coefficient is proportional to the velocity to the power 0.8 or 4/5. Okay. Now, as I said, there is something called a transition Reynolds number, and which will happen when the length of the plate is long enough, so that the Reynolds number exceeds the critical value, right. So, till that length the flow is laminar followed by turbulent, and in such a case this is the correlation that is used. If it is laminar throughout, correlation the top one. If it is turbulent throughout, how will you do that? Well, you can have some mixed air, you can have some mixing, some turbulators, etc. We will come to that. Okay. You can actually introduce a disturbance over here and what is called trip these boundary layer, so that now there is right after these there is mixing and there is flow churning. Okay. So, that is fully turbulent, but otherwise if you just let the flow develop and finally transition from laminar to turbulent, it is going to do it after a certain length when the critical Reynolds number at that point is higher, when the Reynolds number is higher than the critical Reynolds number, and the correlation to be used is the third one. Flat plate with unheated length. What is that? That is a case when, sorry, you have a flat plate like this, you have air coming in, but you start heating after a certain length. Sorry. So, therefore, what happens? The momentum boundary layer develops right from here, but the thermal boundary layer starts developing only from this point. So, there is an unheated length, as you can see, this is an unheated length. If that is a situation, which is actually quite common, if it is a circuit board, so the air is moving over the circuit board and then you have a component which is heated, it is not uncommon. If that is the case, you use this correlation. This unheated length zeta, okay, this unheated length zeta is given by this correlation. You first get a correlation for Nusselt number from the top 3, assuming that zeta is equal to 0, and then you basically use 1 minus zeta over x to the power a the whole to the power b, and these a and b are standard values that are available. Okay. I have this table which gives you a, b, c and m values, you can see here. So, c and m, laminar, isothermal 0.332, which is x actually, the average is 0.664. So, these are all well documented. Okay. If it is flow over a cylinder, the Nusselt number however now becomes NuD. So, Nusselt number, oops, sorry, I do not know where this came from. If it is flow over a cylinder or a sphere. Okay. And similarly, Reynolds number will be rho u d over mu. If it is an isothermal array of cylinders, then it is a little complicated as is shown over here, and C m, C2, all these correlations, all these coefficients, all these indices, there are standard values and lookup tables available for these. Okay. So, you just need to know that these correlations are available and these values will be given to you. Again, I repeat, the challenge is to use the correct judgment, or is in the judgment of using of choosing which correlation to use. Internal flow, force convection, internal flow. So, these were all external flows. So, flow is happening over the body, whether it is over a sphere, over a cylinder, over a plate. Now, if it is flow through a channel or a pipe like this. So, if it is a circular pipe, the Nusselt number, which is again NuD, sorry, h d by k, and d is the ID, internal diameter. Okay. That Nusselt number value comes out to be constant, 3.66 and 4.36, whether it is isothermal boundary condition, which is constant temperature, or isoflux boundary condition, which is constant heat flux. It is for laminar flow. If it is a turbulent flow, then Nusselt number, this is a very famous correlation called Ditus-Boelter, 0.023 Reynolds to the power 4/5, Prandtl to the power either 0.3 or 0.4, depending on if the wall is heated or if it is cooled. So, whether it is heat being transferred from the heated wall to a colder fluid, or whether it is a heat or wall getting heated up because a hot fluid is flowing through it. Okay. Now, here let us spend a little time on the flow physics. Here also there is a thermal boundary layer that happens, or that takes shape, but that if this is one of the cross section, you see there is a thermal boundary layer that happens on this wall, the top wall, as well as the bottom wall, and beyond a point they intersect. And as they intersect, the temperature profile therefore at the beginning goes from the wall temperature to the fluid temperature at both walls, and finally it takes this paraboloid profile. Okay. Now, the question is, what happens if you use non-circular tubes? So, for non-circular tubes, what we do is we use something called a hydraulic diameter dH, which is given by 4 times area divided by wetted perimeter. Okay. So, let us go over here. What will be dH for a square? It is 4 a squared, 4 times area. So, the flow is, this is the cross section of the pipe, right, instead of a circle. 4 a squared over 4 a equals to a. What happens if it is a rectangle? Think about it, this is very similar to flow between two fins through a channel. Then what happens? 4 AB divided by 2 into A plus B. Okay. What happens if B is much greater than A? Then dH becomes what? 2a. Why? You divide everything by b. Okay. If you divide everything by b, then what happens? It's 2a divided by a by b plus 1. A by b close to 0 because b is much greater than a. So, it is 2a. Okay. So, this is a classic case of what is called a micro channel. All right. Okay. Let us move back. So, for hydraulic for non-circular cross sections, use hydraulic diameter. Okay. Let us quickly go through natural convection here also. If it is a vertical flat plate with, and here gravity is important. So, what happens? The flow here becomes lighter and it moves up, and as it moves up it carries heat away. This is how the temperature varies, and if I draw, this is how the velocity varies. It is a little different from forced convection, because here the maximum velocity occurs somewhere within the boundary layer. There is no within this range, and the thermal boundary layer, of course, it's again this is kind of the value, okay, highest at the wall and then slowly becomes equal to the ambient temperature. Okay. So, here also we have correlations like this, except now these are in terms of Rayleigh number. Nusselt is a function of Rayleigh number, and L is the height of the plate here, because this is the flow direction, correct. So, this is L. Vertical flat plate, if it is a horizontal flat plate, then these are correlations. Horizontal flat plate is the hot surface facing up, then the flow will go up. If the hot surface is facing down, okay, and so these are the same thing. If it is a cold surface, then this and this is the same, okay. But if it is facing down, what happens? The flow cannot leave, right. So, therefore, this is the correlation, it is almost half, as you can see, because the hot fluid wants to rise, but it cannot because the plate is blocking it. So, it has to go around and go up. So, these are the correlations. Long horizontal cylinder, again Nusselt as a function of Rayleigh number. Sphere also Nusselt as a function of Rayleigh number. Natural convection through vertical channels, very important, because for heat sinks, if it is vertical channel, then look at it, it is a complicated correlation, but do we know everything? Nusselt as a function of spacing, where S is the space between, S is the spacing, okay. It is a correlation of Barkhorn and Rosenau. S is the spacing between, S is the spacing, L is the length, and W is the total width. Then what happens? For isothermal plates, this is the condition where the temperature is the same, C1, C2 needs to be found out, and for isoflux plates, instead of Rayleigh number, because Rayleigh number you need delta T, but you do not have a Ts here, it is an isoflux. So, this is a different definition, NuSL and Rayleigh star, all right. And then this is how you use it. See, if the heat flux is given to you, you can calculate Rayleigh star, okay, and then you can find out the Nusselt number, and from there you can find out the temperature at the position where at the what is it, the top of the plate, which is where it is going to be highest. Okay. So, these numbers, what is C1, what is C2, they are all given here. Optimal spacing, this is important. What is optimal spacing? Look, and this is where S max and S opt, these are important. S max is, look, when you have two surfaces next to each other, if you move them far apart, then the heat transfer from one plate is the highest, because it is not disturbed by the presence of another hot surface next to it. If you bring them very close, then of course, this hot plate influences the heat transfer from the adjacent hot plate. Okay. So, S max is when beyond a point this plate does not even feel the presence of this plate, and that is when these boundary layers that we saw 2 slides back, I am sorry, Oh, okay. The boundary layers that you saw 2 slides back, there will be a boundary layer on this surface, and if you have another one next to it, there will be another boundary layer. When these boundary layers do not overlap, then that is the optimal spacing, where the heat transfer from this plate is going to be maximum, right. But then for a given W, that is not good, right, because then you can only accommodate that many number of fins. Your heat transfer per plate is higher, but number of plates is less. On the other hand, if you bring them closer, heat transfer per plate is lower, but number of plates is higher, or per surface is lower, but number of surfaces is higher. Every additional fin means 2 additional surfaces. So, then there is an optimal spacing, which is going to be a function of the length, because the boundary layer also increases with increasing length. So, that is what is given over here. So, understand. So, S max is the maximum heat transfer from one heated surface, and that happens when the two adjacent surfaces are so far apart that the boundary layers do not intersect at all. So, it is just at that point when they do not intersect, they are just probably touching at the top end, that is it. Beyond that, if you move them apart, does not matter, the heat transfer per surface does not change, because right at that S max itself or higher, one surface does not know that the other is present. But if you bring them closer, heat transfer per surface goes down, but number of surfaces go up for a given width, right. So, therefore, there is an optimal spacing that exists. So, S opt and S max is different, and as you can see, S max is greater than S opt, and it is really for isoflux conditions that ratio is quite high, almost 5 times. Clear? All right. So, that kind of wraps up our discussion on heat transfer correlations. We looked at various correlations, and these are correlations that we are going to use. Okay. So, if it is for example, a finned heat sink under natural convection, we are going to use the Barkhoven and Rosenau correlation, which we saw in the last slide. If it is flow through a finned heat sink, I will take each of these, the space between 2 adjacent fins, as a channel and use the internal flow correlation for either whether it is laminar or whether it is turbulent. Okay? And from there I will get the Nusselt number. Use hydraulic diameter, by the way, because that is a non-circular cross sectional geometry. Clear? So, this is how we get the average heat transfer coefficient. I know what is going to be my thermal resistance. Clear? Theta SA. All right. Okay. Thank you very much. In the next class, what we will do is we will quickly talk about how do we calculate also pressure drop. There is a correlation for that as well, and then move on to thermal, some thermal technologies other than heat sink. Okay. Thank you very much, and see you in the next class. Bye bye.